Last lesson of chapter 14.8 in multivariable calculus, we're going to use Lagrange multipliers for two constraints. So today we learn how to find the maximum or minimum values, and by the way, when we're talking about that of course is implying absolute max and absolute minimum values of a function, but we're given two restrictions. We're looking for the extreme values of f when it's restricted to lie on a curve C where two level surfaces intersect. So we've got two constraints. G and H have to be satisfied. So we've got two constraints here. So here's what's going on. If we were to graph where G and H are intersecting, they would intersect at a curve C. And you can see in this picture, I've actually already highlighted that curve C in red. So, you can see that's, more or less coming this way. You could say, all right, so that curve is satisfying the points where G would equal K and H would equal C. But remember, now we'd like to say just on those points where we're assuming that F would also be located, we'd like to find where F would be the absolute biggest and smallest. This picture right here really describes what's happening. As we begin to look at F here, you can have a gradient of F coming out right here. But you can see, I've just really photocopied this from our book. You can see that we've got G, gradient of G and gradient of H in the mix too. Way earlier in the year, we learned how to add two vectors together, like vector A and vector B. We said that with the parallelogram method, this diagonal of the parallelogram would be the sum. You look at that and you might think, wow, if this is the picture at hand, it sure looks like the gradient of F would be the sum of gradient of G and gradient of H. Well, yes, some scalar multiples of them. So in this box is the key to doing this problem. The gradient of F is the addition of some multiple of the gradient of G, that's lambda, that should look somewhat familiar, plus, now this is the Greek letter mu, so that's mu times gradient of H. So it's that addition of vector idea that's going on. It's just that we might have to lengthen the vector of A and B in this picture right here to be able to arrive at the proper diagonal. So, of course, just like we did in the past, we're going to deal with a system of equations. And now we'll have two constraints that will be thrown into that system. So let's get started right here on a problem. There's only one, but of course, it's going to be rather involved. As you look here, you could say, well, G is going to be your x plus y plus z equals 1. And your H is going to be your other constraint. That's x squared plus y squared. We also want that to just equal a 1. But I'm going to have to find some gradients, and we're going to get to that in a minute. So let's read the problem here. Find the points that are closest to and furthest from the origin that are on both of the following regions. So we could say here's x comma y comma z, satisfies both of these equations. So x comma y comma z would be on the curve that satisfies both of those equations. Now, I'm also going to be trying to see, so here's my curve. Imagine it's like that red curve that we see right there. We'd like to know which point on it would be closest to or furthest away from the origin. Well, starting us off, we could say that sure looks like the distance formula. And we could say, well, that's going to be x minus 0 quantity squared. Here we'd have y minus 0 quantity squared. And then we could say z minus 0 quantity squared. When they're saying find the closest and furthest, we're trying to make little d as big and as small as possible. Now, of course, what we've done in the past is we said, hey, look, let's instead look at d squared. And d squared, I'm going to call f. And f is just going to be the exact same basic premise that we have here without the square root. And my goodness, that's such a much, much nicer looking kind of a setup. So listen, we're going to go ahead and find some gradients here. Let's go ahead and find the gradient of f. Derivative of f with respect to x would be 2x. The derivative of f with respect to y would be 2y. And the derivative of z with respect to z here, or f with respect to z, is 2z. And kids will say, hey, that's not so bad. I definitely hope not. Let's take a look at the gradient of g. Maybe one of the nicest gradients that you could ever ask to see here. What would that be? 1, 1, 1. The derivative with respect to x, y, and z, they're all 1s. And then, very nicely, we could say, well, my goodness, how about the gradient of h? Well, the gradient of h here, well, again, we need the derivative of this x squared plus y squared. With respect to x, we'd get 2x. With respect to y, we'd get 2y. How about with respect to z? 0. Oh, that might just turn out to be quite handy. Now, if you look at the top of the screen here, you know, this right here is the key. This, without a doubt, is where we're going. The x component is going to be related to the x components in these other gradients. The gradient of f is going to be what we call a linear combination, this multiplication here. So I could real quickly say, well, I'll have 2x, looking at my x component. We're going to say take lambda times the x component of g, plus then I'm going to have mu times the x component over here. That would be a 2x. So that's one of the equations in my system. And then I'm going to say, well, hold on. We also have, for our y component, I'll have 2y. Well, that's going to be lambda times 1 again. Wow, that's seeming very familiar. Plus a mu times a 2y. And then finally, we'll have a 2z. And with 2z, this one's going to be 1 lambda. And then we'll say plus mu times 0. And mu times 0 is just going to completely disappear. And that is maybe one of the most critical parts of the problem right here. That really can unlock some solving choices for us. But please do understand, guys, that our constraints are also a vital part of the system of equations. We're going to say, remember that any point on f here is satisfying g equaling 1. It's also satisfying that h, which is your x squared plus y squared, would equal 1. So here's what makes these problems tedious. Without a doubt, you're going to see a lot going on here. You can see that we've got 5 different equations that we've just written down. 5 of them. But maybe the one that should jump out at us the most is the utter simplest. And you don't always get this, but thank goodness it does show up with some regularity. You could say, my goodness, I know that lambda is really just 2z. That z component equation really is simplified a lot. What does that mean? It means that everywhere where I see a lambda, I can substitute. So I'm going to do that. I'm going to real quickly say lambda is really 2z. And no doubt about it, you know, that doesn't mean that this problem has just become utterly simplistic and now we know what to do to finish the problem up. No doubt there are still quite a few things to take a look at. But look, just looking at the gradient system part where we were setting up our x, y, and z components, right now life has gotten at least a little bit simpler. And I think without a doubt someone can very quickly say, well, wow, look at all those 2's. Could we not divide out a 2 from every single one? Of course we could. Well, look, there's more to this story, though. As we're looking right here, you could think, well, wow, where could we be going with this? Both of these have a z in them. Both of these have a z. That seems to be some common ground. You could say, well, z right here would be x minus mu x. And right here, you could say z would be y minus mu y. And, substituting, we could very quickly just come up with this equation that x minus mu x would equal y minus mu y. Now, at first glance, you might think, is that of any help? Actually, I think it is. I really do think it is. Let's think about this just for a moment. I could do a little bit of factoring. I could pull an x out, and I'd have 1 minus mu. I could factor. I could pull a y out, and then I'd get 1 minus mu. Any observation? We could cancel out a 1 minus mu as long as mu was what? Not equal to 1. So here's the big star. If, big if, mu is not equal to 1, then we get x is equal to y. It's like dividing those out. That's a very huge condition. Because someone could very quickly say, well, wait just a moment. Is it not possible that mu could equal 1? It is possible. We're not done with this aspect of the problem. But right now, you could say, now wait just a moment. Let's just assume that mu wasn't equal to 1. Then x is equal to y. The kids will say, so? Well, if x is equal to y, I'm going to go up to a constraint that only involves x and y to begin with. I'm going to say, look, if we had x is equal to y, which is a valid possibility, that means x squared plus x squared now, if y was just equal to that, that would be a 1, and I'd have 2x squared would equal a 1. And all of a sudden we could say x squared would equal 1 over 2. Would you agree with me then that x would be plus or minus 1 over radical 2? Are we okay with that? Well, right now, you also know what y would equal. Why? Because the y value has to be the same thing. So we could say, here's a case that we could have at hand. We could say, case number 1, we could say x is equal to 1 over root 2. Well, guess what? Your y would have to be exactly the same thing. And we could say, here's another case, case 2. We could say, well, what if x was that negative? Well, remember, y is exactly the same thing. But do you think we might be able to find out what z is? Well, wait a minute. Take a look up here. We've got a second constraint. We've got a second constraint here. And we could say pretty quickly, now what if x was equal to 1 over root 2 and y was equal to 1 over root 2? Could we find out what z was? Well, this would become 2 over root 2 plus z equals 1. And then z would equal 1 minus 2 over root 2. Now, of course, sometimes kids will wonder if it's okay to rationalize here. And in fact, I do think it's a smart thing to do right here, because you'd get 2 over root 2 all over 2. You'd say this would be z equals 1 minus root 2. And of course, your 89 could reduce that just as well. Hey, I've got 3 coordinates. I've got a point that I can look at. I think our video's about